12.2. Representing Boolean functions. So we know that f of x1 to x2 up to xn is equal to some sort of expression of the xi's 0, 1, and or plus dot complement. Operations, bits, variables. On the other hand, if I would make a table where this is x1, x2, up to xn, if we started off with all zeros and then we ended up all with ones, we would have 2 to the n rows here. And then if I would write my function, f, this would either have a 0 or a 1 all the way down to a 0 or a 1. In other words, this would be a column of zeros and ones. But because of this physical representation, that tells us that this particular column has 2 to 2 to the n total possible tables. I'm going to pick a 0, 1, 2, or a 0, 1, 2. Sorry, no, I shouldn't have said or. 0, 1, and a 0, 1, and a 0, 1, right? So it's 2 times 2 times 2 times 2 for every single one of those. So it's 2 times itself, 2 to the n times, so it's 2 to the 2 to the n. So that would tell us things like, I don't care what function you give me. If I would have simply x and y, which would be 0, 0, 1, 1, 0, 1, 0, 1, this particular function, right, would be a 2 and a 2 and a 2 and a 2. So this particular table, whatever exists here, would be simply 2 to the 4th. 16 total possible tables. That's it. There's only 16 tables that would ever exist, period. If I had just simply an x and a y, I could write all 16 of those tables. What would they be? All zeros, a 1 with zeros, a 0 and a 1 with zeros, right? You just, however you want to represent all 16, we could make them all in a nice little table, right? A big table of tables. There would be 16 of them, but if f of x1, x2, up to xn is an expression, so this thing's an expression. How do you make expressions? You write variables, you write operators, and you write zeros and ones. How many ways can you do that? If you think about it this way, if I gave you a keyboard that only had x, y, plus dot complement 0, 1, and that's your entire keyboard. And I said write, and I would make you write it in infix notation. All right, so I need parentheses, sorry. So parentheses for grouping symbols so that we understand it. How many things could you possibly type out? Countably infinite. There's countably infinite expressions that you could create. But all of those expressions, when I wrote the table, would be what? One of those 16. So you have a countably infinite expressions, but there's only 16 tables. For this one, since it's 2 to the n, right, I would have countably infinite expressions, but there's only 2 to the 2 to the n, which is finite. It's a number of tables that even exist. Here's a good question. I'm saying this is countably infinite. Anybody remember why? Anybody remember that proof? from the countability of rational numbers, the idea behind this? When I make an expression, how many choices do I have for when I make an expression, what do? I have to pick a symbol from my first symbol, right? Which could be what? Left parenthesis, right parenthesis, symbol. If there's n symbols, right, it would be n of those. And then plus, and then times, and then negate, and then 0 and 1. Right? So that would be 7 plus n, right? There's going to be 7 plus n. For the first character I can touch, there's 7 plus n of them. That's finite. Then what do? I hit the next character. But that is finite. And then I hit the next character. That is finite. A finite group, even if it's infinite, if I never stop, of finite things is countable. A countable collection of finite things is countable. A countable collection of countable things is countable. So it's countable. But it's still infinite. So that kind of gets to the question of, if the table is what matters, if I was given the table, could I find a function equal to an expression that makes that table? So, for example, if I said x and y, and I went and I looked at my function, I noticed I had 0, 0, 1, 1, 0, 1, 0, 1, and I found that this is 0, 1, 0, 0. My question would be, could you give me an expression? You have the table. You know what wants to happen. What's supposed to happen? What's supposed to happen is this thing only spits out a 1 if the first object is a 0 and then the second object is a 1, and this better spit out a 1, and that's the only time this spits out a 1. Every other time this thing will spit out a 0. Can you make an expression? Well, the answer for this would be, how many expressions would exist? A countably infinite number of them. Well, let's narrow it down. I don't want a countably infinite number of them. I want an answer that you can come up with and an answer I come up with, and we can agree that the answer is the same between the answers that we came up with. So we have to limit this expression. So step 1 is, because possible expressions are infinite, we're going to narrow it down. We're going to narrow the type of expressions because we have an infinite possibility of them. Countably infinite, but infinite, so we got to narrow it. This, just simply making things up at the top of your head won't work. First thing that we're going to do is we're going to need some terms to work with. Step 1, a literal. What's a literal? A literal is either x or x bar. It's a variable or a variable's complement. The second term that we can work with here is called a minterm. What is a minterm? A minterm is a product of all the literal variables. I'll just say of all the literals. So example, if f is equal to x, y, and z, we would have 8 possible minterms. I could have x, y, z. That's a product of all of those, but I could do them in literal form. I could do x bar, y, z. I could do x y bar z or x bar y bar z. I could do x y z bar or x bar y z bar. Or I could do x y bar z bar or x bar y bar z bar. Those are all possible. What do I want? I want all the variables in product, but as a literal, which means I either have an x or an x bar. Why do I know I have 8? For me to make a minterm, I need to pick either x or x bar, 2 choices, and then a y or y bar, 2 choices, and then a z or z bar, 2 choices. Another thing that we can look at here would be a max term. A max term is the sum of all literal variables. Again, if I had an example, if I had f of x, y, z, we would have 8 possible max terms. What are the 8 possible max terms? I could have x plus y plus z. That's the sum of just simply the x's. Or I could have x bar plus y plus z. Or I could have x plus y bar plus z. Or x bar plus y bar plus z. Or x plus y plus z bar. Or x plus y plus, x bar plus y plus z bar. Or x plus y bar plus z bar, or x bar plus y bar plus z bar. Notice it's the same ones, except I do pluses. So these are the 3 things that we need to recognize. We need to recognize what's a literal, what's a minterm, and what's a max term. What's nice about these is a little feature. Note, if I give you A plus B plus C, I have associativity because it's all plus, right? So I could do that, or I could do that. I have commutativity. I could take the B and the C and switch the order, right? So I don't need parentheses. Why do I not need parentheses? Every one of the trees for this particular infix expression would all evaluate the same thing because it's associative and commutative. Doesn't matter. But I see plus everywhere. What is x plus things that give you x? All right, that's a do nothing, right? What's an x plus 1? That's a dominator. So, knowing that I have the identity in the domination, let's look. This is a max term, right? So if I had A, B, and C, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Consider A plus B plus C. Oh, I'm out of time, aren't I? Garg! So, finish this. And then look to see if there's something special. Is there one row that has this particular type of meaning that all the other rows have some other value? And the question is, why? Why? Why from domination identity does this column become so weird? And we'll use that to do sums of products and products of sums next class. All right, that's it. Sorry.